iron evaporates from the surface on the day side, gets carried by winds to the night side, cools and falls as liquid iron rain. Subscribe if you want more of the cosmos. This is White Space. Settle in. The universe does not distinguish between the beautiful and the lethal. It builds both with the same indifferent physics, the same handful of elements, the same forces that hold electrons in orbit and keep galaxies from dissolving into darkness. There is no category in the laws of nature reserved for things that are safe. Gravity does not moderate itself near inhabited worlds. Radiation does not spare the fragile. Temperature does not plateau at survivable levels out of consideration for what happens to live near it. The universe is not hostile. It is simply complete, and completeness, applied without limit, produces conditions that the word dangerous cannot adequately describe. Every object you will encounter on this journey exists right now, somewhere in the observable cosmos. Each one has been measured, catalogued, and studied from the greatest distance that instruments allow. None of them are hypothetical. None of them are extrapolations beyond what observation has confirmed. They are real places orbiting real stars composed of real matter, and none of them would permit you to survive long enough to understand what was happening to you. We leave Earth behind. We leave behind the atmosphere that shields us, the magnetic field that deflects charged particles, the moderate temperatures that keep water liquid, the comfortable distance from a well-behaved medium-mass star that has burned steadily for 4.5 billion years without incident. We leave behind everything that makes the word home meaningful, and we travel outward through distances so vast that the speed of light itself becomes inadequate. Distances where even that universal speed limit produces travel times measured in centuries, millennia, tens of millennia. We travel in the only way that physics permits across such spans, with patient observation, with instruments tuned to the faintest signals, with mathematics that can reconstruct a world from the way a distant star dims by a fraction of a percent for a few hours at irregular intervals. Tonight we ask a simple question: what does the universe look like when it reaches its extremes? The answer begins 3,000 light years from Earth, in the direction of the constellation Cygnus. Here, a gas giant traces one of the strangest orbits ever recorded. The planet designated Kepler-16b does not circle a single star. It circles two of them simultaneously, a pair of stars locked in mutual orbit, pulling at each other with every passing second, their combined gravity reshaping the space around them into something more complicated than any textbook diagram of an elliptical path. One star is a K-type orange dwarf with about 69% of the Sun's mass. The other is a red dwarf with only about 20%. They orbit each other every 41 days, separated by roughly 33 million kilometers. And around this binary pair, at a distance of 104 million kilometers from the common center of mass, the planet Kepler-16b completes its year in 229 days. From the surface of any hypothetical moon orbiting this world, the visual experience would be unlike anything in the solar system. Two suns would rise each morning. Not simultaneously, not identically. The orange dwarf would outshine the red one by a significant margin, but both would be visibly distinct sources of light, their relative positions shifting from day to day as their mutual orbit proceeds. Periodically, one would pass in front of the other, as seen from the planet, producing eclipses that change the quality of light falling on the surface. The shadow geometry would be complex, shifting never quite the same twice. A human standing in an open field under those two stars would cast two shadows simultaneously at slightly different angles, one sharper and one softer, both moving independently. The stability of Kepler-16b's orbit is remarkable, precisely because circumbinary systems are dynamically treacherous. A planet placed too close to a binary pair is flung outward by gravitational perturbations before it can fully form. A planet placed at precisely the wrong resonance, with the binary orbital period accumulates destabilizing energy kicks until it departs. Kepler 16b sits just outside the inner boundary of the stable zone, the closest a planet can orbit while maintaining long-term orbital integrity. Move it slightly inward and the simulations diverge into ejection or collision within a few million years. Move it slightly outward and stability improves, but the planet receives less heat and the system's architecture changes. The planet exists at a precise location, not by coincidence, but because planets that formed closer were removed by instability, and this one survived. The discovery of Kepler 16b, announced in 2011, was the first confirmation that planets can orbit two stars. Before that, the idea had existed only in science fiction. After it became a surveyed fact. At least a dozen confirmed circumminary planets have since been identified, each with its own particular arrangement of stellar masses, binary separation, and planetary orbit. Kepler 34b, for instance, orbits two nearly identical Sun-like stars every 289 days, a more symmetric version of the same architecture. Kepler 47 is a three-planet circumminary system, the most complex confirmed so far. The category has moved from exotic to merely uncommon. But uncommon still means that these worlds exist in gravitational environments our solar system has never experienced, governed by dynamics that no single planet around a single star ever encounters. 190 light-years from Earth, a planet orbits a yellow star in a manner more closely resembling a comet than anything in our solar system. Its designation is HD 27782b. The orbit is so elongated, so compressed into an extreme ellipse, that the planet spends most of its year in cold, distant space, then plunges inward to pass its star at terrifyingly close range before swinging back out again. The eccentricity of this orbit, the standard measure of how far an ellipse deviates from a circle, is 0.97. A circular orbit scores 0. An object in a perfect parabolic escape trajectory scores exactly 1. HD 2007b at 0.97 sits within 3 percentage points of ceasing to orbit at all and simply departing the system on a one-way trajectory. It does not depart each time. Gravity catches it at the far end of the ellipse and slings it back. At its most distant point from the star, the planet is roughly 2 astronomical units out, similar to the distance of Mars from the Sun. The temperature of its upper atmosphere at this point may be several hundred degrees below zero. Whatever chemical species can condense at such temperatures do so, forming clouds of frozen compounds that temporarily stabilize the atmospheric structure. This calm lasts for the majority of the orbital period. Then the approach begins. The planet accelerates toward its star, gaining speed as it falls deeper into the gravitational well. The stellar flux it receives increases as the inverse square of the distance, so as the distance halves, the radiation quadruples. Over the course of several weeks, the incoming energy increases by a factor of approximately 2000. The upper atmosphere heats faster than it can conduct that heat to lower layers. Pressure builds asymmetrically. The condensed cloud layers explosively evaporate. The atmospheric circulation, which had achieved some rough equilibrium during the cold phase, shatters into supersonic chaos. Atmospheric models of extreme eccentricity gas giants suggest wind speeds during the close approach phase of several kilometers per second. Shock waves propagate around the planet's circumference, colliding and reinforcing on the night side. The planet heats, expands, loses some fraction of its uppermost atmosphere to the stellar wind. Then the close approach is over, a matter of hours at the deepest point, and the planet retreats. The cooling process that follows is slower than the heating, and the atmosphere spends weeks rebuilding the structures that the stellar encounter destroyed. Over geological time, the cumulative effect of these repeated impacts shapes the planet's chemistry and atmospheric composition in ways that a planet on a circular orbit would never experience. How HD 2782b came to occupy such an extreme orbit is a matter of ongoing research. The most likely explanation involves a gravitational interaction with another massive body in the system's past, a close encounter with a second planet. Now gone, that transferred angular momentum asymmetrically and drove both objects into new, more eccentric orbits. One may have been ejected from the system entirely, the other remained on a path that verges on escape with every orbit. This is a common outcome of gravitational scattering events in young planetary systems. And it may explain why highly eccentric giant planets appear more frequently in systems that lack other large planetary companions. 390 light-years from Earth, a world called Khazau 7b was the first confirmed rocky super-Earth ever found, and it is among the most extreme terrestrial environments known to science. The planet orbits its star in 20.4 hours. Its distance from the star is less than 2.5 million kilometers, roughly 60 times closer than Earth is to the Sun. At that distance, the stellar flux on the day side exceeds 80 times what Earth receives. The surface temperature on the illuminated hemisphere has been calculated at approximately 2,600 degrees Celsius. That is above the melting point of every common rock-forming mineral. The surface is not solid. It is liquid. The day side of Khazau 7b is covered by an ocean of molten rock, not magma in the terrestrial sense, seeping through volcanic vents, but a continuous surface-wide ocean of material that on Earth would be found only deep inside the planet's mantle. The concept of a shoreline, a beach, a coast is meaningless here. The entire illuminated hemisphere is submerged. The atmosphere, such as it is, consists of rock vapor. At 2,600 degrees, minerals vaporize directly from the surface of the magma ocean and rise into the overlying gas. This creates a mineral atmosphere, clouds of vaporized sodium, potassium, silicon, and oxygen, carried by convective circulation from the hotter equatorial regions toward the cooler polar zones. At altitude, the vapor cools, it condenses, and it rains back down as droplets of liquid rock or as hailstones of solidified mineral depending on the temperature gradient at each altitude. This is the weather system of Khazau 7b, evaporation of molten rock from a magma ocean on the day side, atmospheric transport of the resulting vapor, condensation and precipitation of rock on the night side, and the slow return of the solidified material through geological processes over millions of years. The night side is frigid by contrast, temperatures potentially dropping below the freezing point of carbon dioxide. The contrast between the two hemispheres is permanent, because Khazau 7b is tidally locked. The same face always turns toward the star, and the same face always faces away. There is no rotation, there is no daily cycle. The day side has burned in uninterrupted stellar radiation for as long as the planet has existed. The night side has been in permanent darkness for the same span of time. Between them, a narrow terminator zone, a ring of twilight perhaps a few hundred kilometers wide, marks the boundary between vaporizing rock and frozen darkness. 290 light-years from Earth, the planet 55 Cancri E presents a similar class of extremity. It is a super-Earth with a mass approximately 8 times that of our planet, and a radius nearly twice as large, meaning its surface gravity is roughly twice what a human would experience on Earth. It orbits its star every 17.7 hours at a distance of less than 2.3 million kilometers, even closer proportionally than Khazau 7b to its own host. The surface temperature on the day side reaches approximately 2,400 degrees Celsius, sufficient to maintain a surface magma ocean. So far, the profile is familiar from the previous world, but the interior of 55 Cancri is where the story becomes unusual. The system in which this planet orbits, designated 55 Cancri, a binary pair consisting of a sun-like star and a red dwarf, is known to be rich in carbon relative to its oxygen content. Standard planetary formation models applied to carbon-rich systems produce a different interior composition than what is found in solar system planets. Instead of silicate rock and iron, carbon planets may contain significant fractions of silicon carbide, graphite, and at high enough pressures, diamond. The interior layers of 55 Cancri, under the temperatures and pressures generated by its own mass, may include a layer of carbon at conditions that produce crystalline structure, diamond, extending across a shell potentially thousands of kilometers thick, surrounding an iron core, under a mantle of silicon carbide, under a surface ocean of liquid rock. The planet may contain more diamond by mass than any other material except its iron center. It would be a mistake to find this romantic. The diamond layer, if it exists, is buried under thousands of kilometers of material and surrounded by temperatures that would decompose any spacecraft that approached the surface. The liquid rock ocean above it is not calm. 55 Cancri experiences tidal forces from its star that generate internal heating, and its atmosphere, detected through observations of thermal emission, appears to undergo large-scale changes in heat redistribution that have not been fully explained. The planet may be geologically active in a way that our instruments have not yet characterized. What we know is that it is extremely hot, extremely dense, extremely close to its star, and quite possibly built from the most precious material in the solar system catalog, in quantities that dwarf all human usage of the word abundant. 1,200 light-years distant, in the constellation Lyra, two planets share a solar system in a relationship that orbital mechanics would describe as perpetually near the edge. The system, designated Kepler-88, contains a pair of worlds whose gravitational interaction produces perturbations so large that they were detected not through direct transit timing alone, but through the systematic irregularities they introduced into each other's orbital periods. The concept involved is transit timing variation, the principle that if a planet orbits its star alone, each transit occurs at predictable intervals. If another planet is present and exchanging gravitational energy, those intervals fluctuate. The magnitude of the fluctuation encodes the mass of the perturbing body and the geometry of the interaction. In the case of Kepler-88, the fluctuations were large enough to establish that the two planets were in a gravitational conversation of considerable intensity. The inner planet, Kepler-88b, is the smaller of the two, roughly twice Earth's mass, orbiting every 11 days. The outer companion is more massive, approximately 200 times Earth's mass, orbiting every 22 days. The two orbital periods are almost exactly in a 2-Quan resonance. The inner planet completes 2 orbits for every one completed by the outer. This near resonance means that their gravitational interactions accumulate rather than cancelling, creating large periodic variations in orbital elements. The inner planet's orbit precesses continuously, its orientation rotating in space over timescales determined by the mutual interaction. At closest approach, tidal forces across the body of the inner planet flex its interior in ways that generate heat through friction. The magnitude of this effect depends on the planet's internal structure and rheology, how deformable its material is. But for a rocky body in this configuration, the heating can be substantial. A geologically active planet in this configuration would likely exhibit sustained volcanism, not as a result of radioactive decay, which powers most terrestrial geological activity, but as a direct consequence of tidal dissipation. The energy budget for this process comes ultimately from the orbital energy of the system, energy that is slowly, continuously extracted from the planetary orbits and deposited as heat into the planet's interior. the planets gradually spiral toward more circular orbits as this energy is removed. The process operates over hundreds of millions to billions of years. The system is not in immediate danger of catastrophic rearrangement, but neither is it stable in the long-term sense that our solar system is stable. It is a machine in which orbital energy is being steadily converted into geological activity, and the machine will run until the fuel, the orbital eccentricity, is exhausted. 434 light years from Earth, around a star not yet 16 million years old. A massive body orbits within a disk structure so enormous it has no parallel in the known solar system. The object is designated J1407b, informally called Super Saturn, though the comparison understates the scale. Saturn's ring system extends to roughly 140,000 kilometers from the planet's center. The disk surrounding J1407b extends to approximately 90 million kilometers, a radius comparable to the distance between Earth and the Sun. If Saturn's rings were replaced by this system, they would extend far beyond the orbit of Venus and be visible from Earth's surface as a broad luminous band, crossing the sky from horizon to horizon, brighter than the full moon. The discovery came from photometric monitoring, automated surveys that measure stellar brightness across thousands of stars simultaneously, looking for deeps that signal transiting objects. In 2012, astronomers analyzing archival data from the SuperWASP survey identified a series of brightness reductions in the light from J1407 that lasted for several weeks in 2007. The dimming was not consistent with a single planet passing in front of the star. It was a structured, complex series of variations, each dip corresponding to a different ring passing across the stellar disk. Analysis identified at least 37 discrete rings, each with its own width, density, and opacity. Some rings were nearly opaque, blocking most of the starlight behind them. Others were transparent enough that the star remained visible through them. The outermost ring had a width of several million kilometers. Within the disk, a gap approximately 50 million kilometers wide has been identified. A gap of this scale in a disk of this age is most naturally explained by forming exomoon, a body approximately 80% of Earth's mass, sweeping its orbit clear of smaller debris as it moves, creating the cleared zone through gravitational shepherding. If confirmed, this would be the first exomoon detected in the process of formation. The other gaps and density variations in the disk suggest additional bodies or the early stages of clumping that will eventually produce additional moons. The system is a snapshot of planetary system formation at a stage that our own solar system passed through billions of years ago. The rings will not persist. Over the next tens of millions of years, the material will accrete into moons, fall onto the central body, or be dispersed by the combined gravitational influence of whatever objects form within the disk. From the surface of the hypothetical exomoon at 50 million kilometers from J1407b, the sky would be dominated by arcs of light crossing from horizon to horizon. The rings at that distance would subtend a large fraction of the visible sky. Their reflected light would provide illumination during the moon's night side, not enough to read by, but enough to see the landscape clearly. The color of that light would depend on the composition of the ring particles, likely ice and silicate dust in this young, cold system. The central body of J1407b at this distance would appear as a large disk, much larger than the moon appears from Earth, glowing faintly in reflected starlight. The sky of this world would be among the most visually spectacular in the known galaxy, and among the most temporary. This arrangement, so dramatic now, will be unrecognizable in 50 million years. 718 light years from Earth In the constellation Draco, a gas giant called TRES-2b orbits its star every 2.47 days at a distance of roughly 5 million kilometers. It is the least reflective planet yet found. Where Jupiter reflects about 52% of the light that strikes it, and the Moon reflects about 12%, TRES-2b reflects less than 1%. More than 99 out of every 100 photons that reach its atmosphere are absorbed and converted to heat rather than scattered back into space. The planet is essentially a black sphere, not figuratively but in terms of optical behavior, a near-perfect absorber across the visible spectrum. The absorbing agents in its atmosphere include sodium vapor, potassium vapor, and titanium oxide, the same compounds found in other hot Jupiters, but in concentrations and configurations that produce an uncommonly efficient absorption. The atmosphere is too hot for the highly reflective clouds found in cooler gas giants. Ammonia clouds, which make Jupiter bright, evaporate completely. Water clouds present on cooler bodies do not form. What remains is a clear, dark atmosphere of hot gas, laced with absorbing compounds that collectively trap almost every photon that arrives. The temperature, as a result, exceeds 1000 degrees Celsius. The planet is not cold and dark, it is hot and dark, and the darkness is a consequence of the heat, which prevents the formation of the reflective clouds that would otherwise scatter light away. TRES-2b thus emit light faintly in the deep red at the long wavelength edge of the visible spectrum, where very hot objects radiate their waste heat. The glow is insufficient to be called illumination in any meaningful sense. To the eye, standing in hypothetical proximity to this planet, it would appear as an absence, a circular region of sky darker than the space around it, with a barely perceptible reddish edge, where its thermal emission met the surrounding stellar light. It would look less like a planet and more like a hole. 390 light-years from Earth, the planet WASP-76b demonstrates that the universe can produce not just unusual weather, but weather that belongs to an entirely different category of physical process. WASP-76b is a gas giant roughly the mass of Jupiter, orbiting its F-type host star every 1.8 days at a distance of approximately 5 million kilometers. It is tidally locked. The day side receives an enormous and uninterrupted flux of stellar energy. The equilibrium temperature on the illuminated hemisphere exceeds 2400 degrees Celsius. At this temperature, iron does not exist as a solid. It does not exist as a liquid, it evaporates. Iron vapor rises from the heated atmospheric layers on the day side, is carried by planetary scale circulation toward the terminator, the boundary between the illuminated and dark hemispheres, where the temperature drops enough for the iron vapor to condense. And then it falls as rain. Not water rain, not silicate rain. Rain composed of liquid iron droplets, falling out of the dark atmosphere on the night side and collecting in whatever features pass for the lower atmosphere of this world. The observational confirmation of this process came in 2020, when astronomers using the espresso spectrograph on the Very Large Telescope detected a strong iron absorption signature on the day side of WASP-76b, but not on the night side. The asymmetry was the signature of condensation at the terminator, iron vapor arriving from the day side, cooling at the boundary, and precipitating downward before it could cross into the night hemisphere. The detection was unambiguous. Iron rain is not a theoretical prediction on WASP-76b, it is an observation. The planet has confirmed weather that consists of iron falling from the sky. The night side of WASP-76b, receiving that iron precipitation, would accumulate liquid iron in whatever topographic low points its atmospheric circulation produces. The dynamics of how this iron is eventually returned to the day side through atmospheric transport, through convective mixing, through some other mechanism are still being studied. What is certain is that the elemental cycle operating on this planet involves iron moving between vapor and liquid on timescales determined by atmospheric circulation, and that the temperatures and compositions involved would destroy any solid material humanity has ever engineered. 870 light years from Earth, the planet WASP-12b is in the process of being consumed by its own star, and has been doing so for long enough that the consequences are measurable. The planet orbits its yellow host star every 1.09 days, barely more than once per Earth day, at a distance of only 3.4 million kilometers. This proximity, less than 5% of the distance between Earth and the Sun, places the planet within the outer reaches of its star's extended atmosphere. The stellar corona, the diffuse region of superheated plasma extending outward from the star's visible surface, surrounds the planet partially. Material flows continuously between them. The mechanism at work is Roche-Lobe overflow. Each massive body in a gravitational pair, the star and the planet, has a teardrop-shaped region within which its own gravity dominates. This region is called the Roche-Lobe. When an orbiting body expands, either through heating or through internal processes, to fill or exceed its own Roche-Lobe material at the surface, near the point of closest approach to the companion body, finds that the companion's gravity is stronger than the body's own surface gravity. That material flows toward the companion. In the case of WASP-12b, the planet's superheated, inflated atmosphere extends to the boundary of the Roche-Lobe, and gas streams continuously from the planet's upper atmosphere toward the star. The flow forms a diffuse disk around the star, gradually spiraling inward as it loses angular momentum to radiation pressure and tidal interaction. The transit observations of WASP-12b reveal an asymmetry. The planet takes slightly longer to ingress behind the star than to egress, a signature of the extended gas envelope on the leading side, shaped by the dynamics of the overflow. The planet's atmosphere is clearly not spherical. It is a stretched, distorted structure feeding material continuously to its own star. The estimated timescale before the planet is fully consumed is roughly 10 million years. In geological time, this is brief. We are observing WASP-12b in the last 0.2% of its existence as a planet. After it is gone, the star will carry no record of the encounter beyond a slightly altered chemical composition of its outer layers. WASP-12b's biography will end not with an explosion, not with a collision, but with a slow dissolution, evaporated piece by piece into the star that created it. 63 light years from Earth in the constellation Vulpecula, the planet HD 109733b presents perhaps the most visually deceptive object on our journey. Observed from a distance in the wavelengths of blue light, it resembles Earth in the most superficial sense, a blue sphere against the black of space, suggesting seas, suggesting an atmosphere that scatters short wavelengths the way our own does. The resemblance is entirely superficial and entirely false, and understanding why it is false requires understanding the actual source of the color. The blue of Earth's visible disk comes from two sources: the scattering of sunlight by nitrogen and oxygen molecules in the upper atmosphere, a process that preferentially scatters blue wavelengths, producing the blue sky, and the reflection of blue wavelength light from the ocean surface. Both processes require a relatively calm, relatively cool atmosphere. The blue of HD 89733b comes from silicate particles, crystalline grains of rock, condensed from mineral vapor in the upper atmosphere and held aloft by vertical convection. These grains are small enough that they too scatter blue wavelengths preferentially. But they exist in an atmosphere where temperatures exceed 1000 degrees Celsius on the night side and over 1200 on the day side, where winds reach 8700 kilometers per hour. And where those same silicate grains that produce the gentle blue color are propelled at velocities that would shred any material surface they contacted. The rain on HD 189733b is composed of these silicate grains condensing at altitude and falling through the superheated atmosphere. The droplets are liquid glass, molten silicate falling through supersonic horizontal winds, creating a weather system in which the precipitation moves primarily sideways rather than downward. Any probe that entered this atmosphere would be sandblasted by glass moving at several kilometers per second before it reached the lower atmospheric layers. HD 189733b is tidally locked. Its dayside bakes in continuous stellar radiation from the K-type orange dwarf it orbits every 2.2 days. Its night side, isolated from that radiation, is substantially cooler, though still far above any temperature compatible with liquid water. The temperature difference between the two hemispheres drives the planetary scale circulation that produces those extreme wind speeds. The silicate rain cycle, evaporation on the day side, transport, condensation, and precipitation on the night side, eventual return through lower atmospheric circulation operates continuously, a global hydrological cycle analog in which the working fluid is molten rock. 670 light-years from Earth, the planet Kelt 9b represents a category that challenges the classification boundary between planets and stars. Its host star, Kelt 9, is an A-type blue-white giant burning at a surface temperature of approximately 10,000 degrees Celsius, nearly twice the temperature of our Sun. Kelt 9b orbits this intensely luminous object every 1.48 days at a distance of approximately 14 million kilometers. The planet's proximity to such an energetic radiation source produces conditions that have no analog in our solar system. The equilibrium temperature of Kelt 9b's dayside is approximately 4,600 degrees Celsius. To put this in comparative context, the surface of our Sun is approximately 5,500 degrees Celsius. Kelt 9b is cooler than the Sun's visible surface, but hotter than every known red dwarf star. It is hotter than approximately 80% of all known stellar objects. It is technically a planet. It formed around a star through accretion. It has not undergone hydrogen fusion, and it is gravitationally bound in a planetary orbit. But firmly it occupies the domain that was formerly considered exclusive to stars. At 4,600 degrees, molecular hydrogen cannot exist in its standard form. The molecules are dissociated by the energy flux, broken apart into their constituent atoms. Iron, nickel, titanium, and vanadium do not exist as solids or liquids or even conventional vapors. They exist as metallic ions floating in an atomic gas. The spectrographic signature of Kelt 9b's atmosphere shows clear detection lines for ionized iron, ionized titanium, magnesium, chromium, elements we encounter on Earth as heavy metals, as structural materials, as catalysts, here occurring as suspended atomic species in a planetary atmosphere hotter than the surface of most stars. The structural consequence of this extreme heating is that the planet is inflated. A gas giant at moderate temperatures maintains a certain relationship between mass and radius, with the gas compressed by its own gravity into a dense sphere. At 4,600 degrees, the gas is too hot to be compressed to typical densities. Kelt 9b's radius is approximately 1.9 times that of Jupiter, substantially larger than expected for its mass of about 2.9 Jupiter masses. Its upper atmosphere extends further than planetary models predict, facilitating the stripping of gas by stellar wind and UV radiation. The star is continuously dismantling the planet. Current estimates suggest a mass loss rate of several hundred Earth masses per billion years, fast enough that, given sufficient time, the planet would be stripped to its iron core. The race is between atmospheric erosion and stellar evolution. whether the planet is stripped first or whether Kelley 9 exhausts its hydrogen fuel and expands into a red giant first, sweeping all the inner planets into its envelope. 390 light-years from Earth, around a star designated Het P7, an unusual form of cloud has been identified in the atmosphere of a tidally locked gas giant. Het P7b has a mass approximately 1.8 times that of Jupiter and orbits its star every 2.2 days. The day-side temperature exceeds 2,800 degrees Celsius, and winds carry enormous quantities of material from the day side to the cooler night side. Spectroscopic analysis has identified a condensate in the night side atmosphere consistent with corundum, aluminum oxide, the mineral that forms rubies and sapphires when combined with trace elements. At the temperatures on the cooler night side of Het P7b, aluminum oxide can condense from vapor into crystalline particles. The clouds on this planet are not water, ice, or ammonia. They are clouds of tiny corundum crystals, essentially clouds of sapphire. The visual implication of sapphire clouds in a planetary atmosphere is a pale blue-tinted sky on the night side, as the corundum particles scatter light from the day side's glow. The night side of Het P7b does not receive direct starlight, it faces away from its host. But the planetary circulation carries residual heat and scattered light around the terminator, and the corundum cloud tops reflect and scatter that light and wavelengths characteristic of the mineral. The planet is not permanently blanketed in these clouds. Wind patterns on Het P7b vary over time in ways that have been detected through asymmetries in its phase curve, the variation in brightness as different portions of the planet's surface rotate into view. The variations suggest that the cloud layers are not stationary, but are disrupted and redistributed by the complex atmospheric dynamics of a highly irradiated, tidally locked world. The sapphire clouds shift, reform, thin, and thicken over timescales of days, driven by the same physics that prevents any weather on this planet from being tranquil. 4,000 light-years from Earth, a planet orbits not a star but a corpse. The object designated PSR J1719, BES 1438b, was found through an indirect method of extraordinary precision, pulsar timing. The neutron star at the center of this system is a millisecond pulsar, the product of a specific stellar life cycle path that produces some of the most precisely regular rotating objects in nature. Understanding what this planet is requires first understanding what the pulsar is and how it came to be spinning at 10,000 revolutions per minute when ordinary neutron stars spin down over millions of years. A neutron star forms in a supernova, the collapse of a massive star's iron core compressed in a fraction of a second to nuclear density. The resulting object is roughly 20 kilometers in diameter but contains between 1.4 and 2 solar masses. Its magnetic field is enormously strong, and the field geometry channels radiation into narrow beams that sweep across the sky as the star rotates, producing the characteristic pulses detected from Earth. Newly formed pulsars rotate quickly, milliseconds to seconds per revolution, but they slow down over time as the rotating magnetic field radiates energy away. Over millions of years, a pulsar loses angular momentum and its pulse rate decreases. Eventually, the pulsar becomes too slow and its magnetic field too weak to produce detectable pulses. It goes radio quiet. A millisecond pulsar should not exist according to this life cycle. Stars that are old enough to have completed neutron star formation should be rotating too slowly to qualify as millisecond pulsars. The resolution to this apparent contradiction is binary accretion. If a neutron star has a stellar companion and that companion evolves to fill its Roche lobe, material flows from the companion onto the neutron star. This accreting material carries angular momentum, spinning the neutron star back up to millisecond rotation rates over millions of years. The neutron star is recycled, revived from a dying slow rotator into a fast millisecond pulsar. When the accretion is complete, the companion has been stripped down to a remnant or consumed entirely. What remains is a rapidly rotating neutron star and the stripped core of its former companion. PSR J1719 191438b is that stripped core. What was once a stellar companion, likely a white dwarf of helium composition, had its outer layers continuously stripped by the neutron star's accretion over billions of years. What remains orbits every 2.18 hours at a distance of 600,000 kilometers. Its mass is approximately 300 times that of Earth. Its density exceeds 23 grams per cubic centimeter, denser than osmium, the densest element that exists in bulk on Earth, which has a density of about 22.6 grams per cubic centimeter. The material under this density and at this composition, primarily carbon, at conditions of extreme pressure, is most likely crystalline. The planet is made of diamond, not a thin layer, not a region. The bulk of its interior, under the pressures maintained by its own mass, is in the crystalline carbon phase. This object is a diamond of planetary scale, orbiting a neutron star that spins 10,000 times per second, bathed continuously in pulsar radiation of sufficient intensity to ablate any material less than several kilometers below the surface. 5,000 light years from Earth, there is an object that challenges our understanding of what extreme magnetic fields can do. SGR 1620 is a magnetar, a neutron star whose magnetic field is approximately 1 quadrillion times stronger than Earth's. To put this in perspective, the strongest sustained magnetic fields produced in human laboratories reach about 50 Tesla. Earth's surface field is approximately 0.00005 Tesla. The field of SGR 180620 exceeds 10 to the 11th Tesla. This is not a small incremental step beyond what we are familiar with. It is a class of physical object that operates through entirely different mechanisms than anything in daily experience. Mechanisms in which the magnetic field is so intense that it structurally deforms the vacuum itself through a quantum electrodynamic effect called vacuum birefringence. Magnetars form through the same supernova mechanism as ordinary neutron stars, but with initial rotation rates or field amplification processes that produce an anomalously strong magnetic field. The field stores an enormous amount of energy. This energy is not stable. It is released in periodic events, magnetar flares, that represent the most energetic phenomena in the universe, short of gamma-ray bursts from collapsing massive stars. On December 27, 2004, SGR 1806-20 emitted a giant flare that released in approximately 0.2 seconds more energy than our Sun emits in 250,000 years. The pulse of radiation was detected by Earth's upper atmosphere from 5,000 light-years away. It affected sensitive instrumentation. It ionized the Earth's atmosphere measurably on the side facing the object at the time. A magnetar flare of this magnitude occurring within a few hundred light-years of Earth would be catastrophic for any planetary surface it reached. The environment immediately surrounding SGR 1806-20 is lethal in every direction. The radiation environment, X-rays, gamma rays, charged particles accelerated by the intense field, is sufficient to destroy complex molecular structures at distances that would require a substantial fraction of a light year to attenuate. Nothing orbits this object. Nothing in its local region of space could survive in a form more complex than individual particles. The magnetar itself is cooling, its field decaying on timescales of tens of thousands of years in astronomical terms. This is brief. Eventually, the field will weaken to the point where the object behaves like an ordinary pulsar, then weaker still as it continues to slow. The most magnetically intense objects in the universe are also among the most temporary. The field that makes them remarkable also destroys them. 650 light-years from Earth, in the constellation Leo, there is a star called CW Leonis. It does not look impressive at the distances ordinarily associated with interesting astronomical objects. In visible light, it is obscured by the gas and dust it has ejected over the past 70,000 years, a self-imposed veil that blocks most of the light it emits. To see CW Leonis clearly requires infrared observations which penetrate the surrounding dusty shell. In infrared, it is one of the brightest objects in the sky. CW Leonis is a carbon star, a red giant that has processed large quantities of hydrogen and helium through nuclear fusion in its interior, generating carbon and whose convective envelope has dredged up that carbon to the surface. The result is an atmosphere with a carbon-to-oxygen ratio greater than 1 more carbon than oxygen, which means that all the oxygen is locked up in carbon monoxide, and free carbon exists in the outer layers in a form that can condense and be expelled. The expelled carbon forms the dusty shell that surrounds the star, blocking the visible light and giving it the appearance of a deeply embedded source when observed optically. The radius of CW Leonis is not fixed. It pulsates over a period of 649 days, expanding and contracting as the balance between the radiation pressure and the gravity oscillates through a thermodynamic cycle driven by the instability of helium shell burning in the interior. At maximum radius, the star reaches approximately 560 times the size of the Sun. Placed at the center of our solar system, its surface would extend past the orbit of Mars and reach toward the inner boundary of the asteroid belt. The surface temperature at this scale is only 2,300 Kelvin, cool for a star. Cool enough that the outer layers barely glow red to the unaided eye. Yet the luminosity is enormous, because luminosity depends on surface area as well as temperature, and the surface area of CW Leonis at maximum extent is hundreds of thousands of times that of the Sun. The mass loss from CW Leonis is extraordinary. Every year, the star sheds an amount of material equal to several times the mass of Earth. The accumulated ejecta now form a shell containing approximately 1.5 solar masses of material, extending outward to a radius of 84,000 astronomical units, more than a light-year in radius. The chemical composition of this shell reflects the interior processing of the star. It contains carbon dioxide, water vapor, acetylene, hydrogen cyanide, formaldehyde, and dozens of other molecular species. In the cold outer regions of the shell, where temperatures drop to just a few degrees above absolute zero, complex molecular chemistry becomes possible, the same interstellar chemistry that eventually contributes to the formation of planetary systems and potentially to the prebiotic chemistry of life. CW Leonis may once have had planets. Any that formed in the inner system would have been engulfed when the star expanded from its original configuration. A blue-white star, perhaps 4 times the Sun's mass, into the current red giant. Whatever worlds existed in the zone where liquid water was once stable, if any ever formed there, are now inside the star's expanded envelope, dissolved into its outer layers, their material mixed into the gas that is now being expelled into surrounding space. The planets, if they existed, have already returned to the interstellar medium from which they formed. Within the next 10,000 to 30,000 years, CW Leonis will exhaust the nuclear fuel sustaining its red giant phase. The helium shell source will become unstable past the point of recovery. The outer layers, no longer supported by radiation pressure from the interior, will be expelled in a final intense wind. The remaining core, a white dwarf of approximately 0.8 solar masses, compressed to the size of Earth, will be exposed initially at a temperature of several 100,000 Kelvin. Its radiation will ionize the ejected shell, causing it to fluoresce briefly as a planetary nebula. a symmetrical glowing structure visible across thousands of light years, beautiful and brief, lasting only a few tens of thousands of years before the white dwarf cools enough to stop ionizing the expanding gas. Then the shell disperses. The white dwarf cools, and the sight of CW Leonis, one of the brightest infrared objects in today's sky, becomes unremarkable, a dim white point slowly fading toward eventual darkness over billions of years. 7,500 light-years from Earth in the direction of the constellation Carina. There is a stellar system that may be the most unstable massive object within the Milky Way's immediate neighborhood. Eta Carinae consists of at least 2 massive stars in close mutual orbit. The primary estimated at between 100 and 150 solar masses, making it one of the most massive known stars, and a companion of approximately 30 to 80 solar masses. The pair orbit each other every 5.5 years on an eccentric elliptical path that brings them within 1.5 astronomical units of each other at periastron, comparable to the distance between Earth and the Sun. The primary star of Eta Carinae is so massive that it approaches the Eddington limit, the theoretical maximum luminosity at which radiation pressure outward equals the gravitational force inward. A star at this limit cannot sustain its own structure indefinitely. Its luminosity exceeds the Sun's by a factor of 5 million. Its surface temperature is relatively low for such luminosity, roughly 30,000 Kelvin, because the star is so large. Its radius fluctuates and its outer layers are perpetually near the threshold of being expelled by the radiation pressure from below. In the mid-19th century, Eta Carinae underwent an event called the Great Eruption, visible from Earth with the naked eye in 1843, during which the system temporarily became the second brightest star in the sky. Over a period of roughly 2 decades, it ejected material equivalent to several solar masses, creating a bipolar nebula now visible in detail through modern telescopes. This structure, called the homunculus nebula, is a pair of lobes extending approximately 2 light-years from the central system, with a disk of denser material at the equator. The ejection event was not a supernova, the star survived. It was something else. A luminous blue variable eruption, a class of massive stellar instability that is still not completely explained. The energy involved exceeded what conventional stellar models predicted possible without complete disruption. Eta Carinae is expected to explode as a supernova or hypernova within the next million years, possibly much sooner. Some models suggest it is overdue. The geometry of the system means that when the larger star finally undergoes core collapse, the resulting gamma-ray burst may or may not be directed toward Earth. At 7,500 light-years, a gamma-ray burst aimed at our planet would be devastating to the upper atmosphere, catalyzing ozone depletion and exposing the surface to lethal UV radiation for an extended period. The probability of the burst being precisely aimed at Earth is low. But the system's instability means that partial eruptions like the one in 1843 may recur on shorter timescales. And each such event reshapes the stellar environment in ways that make the next one harder to predict. 10,000 light-years from Earth, in the direction of Sagittarius, there is a star called WR102 that does not belong to any category of stellar object that most people have heard of. It is a Wolf-Rayet star of the oxygen subtype, one of only 9 confirmed members of this class in the observable universe. The class exists as a category because objects of this type were sufficiently unusual that their discovery required the creation of new terminology. French astronomers Charles Wolf and Georges Rayet identified the first 3 members of this class in 1867, noting the anomalously broad emission lines of heavy elements in their spectra, features that indicated not the absorption of starlight by a cooler atmosphere, as seen in ordinary stars, but the emission of light by hot, rapidly outflowing gas. The interpretation was unclear for decades. The internal structure of Wolf-Rayet stars was not explained until the development of modern stellar physics, which established that these objects are massive stars that have lost their outer hydrogen envelopes through intense stellar winds, exposing the hot fusion-processed interior layers to direct observation. To become a Wolf-Rayet star, the initial mass must be at least 40 times the Sun's. WR102 likely began its life between 40 and 60 solar masses. A massive blue star whose interior processed hydrogen into helium, then helium into carbon and oxygen at temperatures and pressures that most stellar interiors never reach. The outer hydrogen layers were stripped by the intense radiation and stellar wind long ago. What remains is the exposed, processed core, a hot, dense, shrunken object with a radius only 60% of the Sun's but a luminosity 380,000 times greater. The surface temperature exceeds 210,000 Kelvin, 36 times hotter than the Sun and hotter than any ordinary star. WR102 holds the record for the highest confirmed surface temperature of any known stellar object. At 210,000 Kelvin, the peak of the thermal emission spectrum lies far into the extreme ultraviolet wavelengths, short enough to be almost entirely absorbed by the interstellar gas between the star and Earth. WR102 is not bright in the visual sense of the word. It is burning intensely at wavelengths our eyes cannot detect and that our atmosphere would block, even if our eyes could detect them. The X-ray and extreme ultraviolet luminosity of this single object would be lethal to unprotected life at distances of hundreds of light years. The ionization zone it creates in surrounding interstellar gas extends far beyond the immediate stellar neighborhood. The stellar wind from WR102 exceeds 5,000 kilometers per second, roughly 1.7% of the speed of light. The particles expelled at this velocity carry enormous momentum. Every year, the wind strips away material equivalent to several Earth masses. Over 10,000 years, a blink in stellar timescales, the wind strips material equivalent to the mass of the Sun. The cumulative effect has produced a gas nebula surrounding the star, ionized and shaped by the wind into complex arcs and shells visible in infrared observations. The nebula contains the expelled remnants of the star's former outer layers, hydrogen, helium, and processed materials, mixed with the interstellar medium that the wind sweeps up. WR102 is at the terminal stage of the Wolf-Rayet phase. The nuclear fuel sustaining the current phase, carbon, oxygen, neon, is being consumed on a timescale measured in thousands of years. When this fuel is exhausted, the interior temperature is insufficient to ignite the next stage of fusion. The core begins to collapse. Within milliseconds, the collapse converts gravitational energy into an outward propagating shock that disintegrates the outer stellar layers and ejects them at a significant fraction of the speed of light. This is a supernova, specifically a type EB supernova, lacking hydrogen in its spectrum because the hydrogen was stripped long before the explosion. Given the rapid rotation and intense magnetic field expected in a star of this mass, the collapse may also produce a focused jet of ultra-relativistic particles, a long-duration gamma-ray burst. Stellar models suggest this explosion will occur within the next 1,500 years. Since the star is 10,000 light-years away, the light from the explosion will not arrive for another 10,000 years after it occurs, meaning the explosion may have already happened. We are observing a star that may no longer exist, seeing light that departed 10,000 years ago from an object that was alive then and may be dead now. The gamma-ray burst, if produced and aimed toward Earth, would arrive at the same time as the optical flash of the explosion, indistinguishable until detected. Earth's distance is sufficient that the gamma-ray burst from WR102, even if aimed directly at us, would not reach lethal doses at ground level. the upper atmosphere would be affected. But it would not be the species-ending event that a burst from a nearby source would represent. What remains after the explosion is a neutron star, an object of approximately 20 kilometers in diameter, containing 1.5 to 2 solar masses of material compressed to nuclear density. The density is so extreme that a cubic centimeter of neutron star material has a mass of hundreds of millions of tons. Protons and electrons are merged into neutrons by the pressure of the collapse. The neutron star that emerges from WR102's death will be born spinning fast, perhaps at hundreds of revolutions per second, carrying a strong magnetic field. If the field is strong enough and the alignment is right, it will emit coherent radio pulses detectable across the galaxy, a pulsar, marking the location of WR102's explosion. It will spin, pulse, and slowly wind down over millions of years, gradually becoming quieter, eventually going dark. The outer layers expelled by the supernova, carbon, oxygen, neon, magnesium, silicon, iron, and the heavier elements synthesized in the brief seconds of the explosion itself, will expand outward as a shell of hot gas. The shell will sweep up surrounding material, heat it, and glow as a supernova remnant for thousands of years before dispersing into the interstellar medium. The heavy elements manufactured by WR102 in its lifetime and in its death will join the broader inventory of interstellar material available for incorporation into the next generation of stars and planetary systems that form from this region of the Milky Way. The gold in any hypothetical jewelry around the neck of any hypothetical being living on a planet near this region billions of years hence may contain atoms that were fused in the last seconds of WR102's collapse, 26,000 light-years from Earth. At the center of the Milky Way galaxy, there is an object whose presence shapes the structure of the entire galactic nucleus. Sagittarius A is a supermassive black hole containing approximately 4 million solar masses of material compressed within a region smaller than the distance between Earth and the Sun. It is not the largest known black hole. That distinction belongs to objects billions of times the Sun's mass in distant galaxies. It is not the most active. Many black holes at galactic centers accrete material at rates that produce quasars visible across billions of light-years, while Sagittarius A is nearly quiescent by comparison. But it is ours. It is the black hole at the center of the galaxy we inhabit. And understanding it means understanding something about the environment in which the Milky Way stars live. The evidence for Sagittarius A was assembled over decades through careful observations of stars moving in the galactic center region. Stars that orbit an unseen mass reveal that mass through their motions, exactly as planets reveal their stars. The star designated S2 orbits Sagittarius A every 16 years, approaching as close as 120 astronomical units from the black hole at its closest approach, moving at approximately 2.7% of the speed of light at periapsis. This is the most precise measurement of the black hole's mass because the orbital parameters of S2 can be calculated with high precision using standard gravitational physics. The orbit is slightly non-Newtonian. General relativistic precession has been detected, confirming that the behavior of spacetime near the black hole's mass is consistent with Einstein's predictions. The environment surrounding Sagittarius A is among the most energetic and complex in the galaxy. Within a few light-years of the black hole, stars orbit at velocities that no star in the outer Milky Way ever reaches. The density of stars in this region is tens of millions of times greater than in the solar neighborhood. Massive young stars O and B, supergiants that should not exist in such proximity to a region where tidal forces would ordinarily disrupt molecular clouds before they could collapse to form stars orbit the black hole in a disk-like structure whose origin remains debated. The tidal disruption radius surrounds Sagittarius A, the distance within which a star would be torn apart by tidal forces before it could fall intact into the black hole, extends to roughly a few hundred astronomical units. Sagittarius A occasionally flares, releasing sudden bursts of X-ray and infrared emission when infalling material releases energy as it approaches the event horizon. These flares last minutes to hours and represent temporary accretion events as gas or disrupted material passes through the innermost stable circular orbit and plunges toward the singularity. In 2019, an unusually bright infrared flare was detected from Sagittarius A approximately 75 times the typical emission level. The cause may have been related to the passage of a known gas cloud, G2, which made its closest approach to the black hole in 2014. The environment of the galactic center is not static. It is actively, if slowly evolving as material from the surrounding star-forming region spirals inward and is consumed. The event horizon of Sagittarius A, the boundary within which nothing, including light, can escape, has a radius of approximately 12 million kilometers. This is smaller than the orbit of Mercury. The 4 million solar mass singularity that defines this boundary occupies a point, a mathematical limit of infinite density at the current resolution of our series. What happens at or inside this boundary is not described by any currently verified physics. General relativity predicts a singularity. Quantum mechanics predicts that singularities of this kind cannot physically exist. The reconciliation of these frameworks remains the central unsolved problem of theoretical physics, and Sagittarius A is a standing monument to that unresolved question, a fact written in the motions of stars that we can observe, but cannot fully explain. The journey ends here, not because the universe runs out of dangerous objects, but because the category of danger that Sagittarius A represents is not quite like anything else we have visited. A magnetar can kill through radiation. A Wolf-Rayet star can kill through stellar wind and ultimately through an explosion. An extreme planet can kill through temperature, pressure, or chemistry. But the black hole offers something additional, a place where the physics we use to describe the danger itself breaks down, where our ability to follow the trajectory of an infalling object ends at the event horizon. Not because the object ceases to exist, but because the geometry of space-time beyond that boundary is not connected to our own in any way that allows information to pass outward. We have traveled to worlds where rock evaporates into atmospheric vapor and rains back down as liquid glass. We have visited planets where iron falls from the sky, where diamonds form in planetary interiors, under conditions that no laboratory on Earth can sustain. We have stood near dying stars that shed their outer layers into the space around them, seeding it with carbon and oxygen and the molecular precursors of biology. We have examined the corpses of massive stars, neutron stars and pulsars and magnetars that carry more mass than the Sun in a volume smaller than a city. We have looked at the most energetically luminous ordinary stellar object known, a Wolf-Rayet star that burns at temperatures 36 times that of the Sun, that will explode within a few thousand years in an event that may already have happened. And we have paused at the gravitational center of our own galaxy, at the supermassive black hole whose presence shapes the architecture of every star system within thousands of light years. None of these objects are hypothetical. Every one of them has been detected, measured, and characterized by instruments that we built and launched and aimed at the sky over the course of a few hundred years. What was once invisible exoplanet atmospheres, neutron star masses, black hole event horizons, has become measurable through the accumulated ingenuity of generations of researchers who decided that the question of what is out there was worth answering regardless of what the answer turned out to be. The universe is indifferent to our presence. It does not arrange its most extreme phenomena for our benefit or our harm. The iron rain on WASP 76b falls whether or not we observe it. The diamond planet around PSR J1719, the 1438, orbits its pulsar in 2-hour cycles. Whether or not we have identified it, Sagittarius A has been consuming material at the center of our galaxy for billions of years without reference to the fact that a planet 26,000 light-years away would eventually evolve creatures capable of measuring its mass by watching stars orbit it. But the indifference is precisely what makes the observation remarkable. We built instruments sensitive enough to detect the transit of an Earth-sized planet across a star thousands of light-years away. We measured the precession of stellar orbits around a black hole 26,000 light-years distant. We detected iron vapor on the day side of a planet and confirmed its absence on the night side, demonstrating that it must be raining. We have reconstructed the interior composition of worlds we will never visit, and the life cycle of stars that died before our planet formed. The universe did not make this easy. It placed these objects at distances that required generations of technological development to bridge. It encoded the information in signals, transit depths, timing variations, spectral lines, gravitational wobbles that required mathematical tools to decode. And it did all of this without knowing and without caring that we would eventually come looking. The journey continues. There are objects we have not yet characterized. There are classes of phenomenon that our instruments cannot yet detect. There are dangerous and extraordinary places in the universe that we do not yet have names for. Each generation of telescopes opens a new window, and what comes through that window changes what we thought we knew. The questions we cannot yet answer are not failures. They are the leading edge of a process that has been ongoing since the first careful observers pointed instruments at the sky and decided that what they saw was worth understanding. We are still looking, we will keep looking, and the universe, vast and indifferent and extraordinary in equal measure, will keep providing things worth finding. There is one more category of extreme object that warrants a pause before this journey closes. It has not been visited by any instrument in the way that a star or planet is visited, by pointing a telescope at a specific location in the sky and gathering the light or radio waves that emanate from that place. This category is defined instead by the absence of light, by the absence of galaxies, by the near total absence of matter. The universe is not uniformly filled. The galaxies and galaxy clusters that make up the visible cosmos are arranged in a web-like structure, filaments of matter surrounding vast regions of emptiness. These regions are called voids, and some of them are so large, so completely empty, that they represent a form of cosmic extreme that does not involve heat or gravity or radiation at all. The Boötes void, located roughly 700 million light-years from Earth in the direction of the constellation Boötes, is one of the largest known structures in the observable universe. It spans approximately 330 million light-years in diameter. To travel across it at the speed of light would require 330 million years. To put this in perspective, the distance from Earth to the nearest star, Proxima Centauri, is 4.2 light-years. The diameter of the Milky Way is roughly 100,000 light-years. The Boötes void is 3,300 times wider than the entire galaxy we inhabit. Within this volume, a sphere with a radius larger than can be meaningfully visualized in human terms, there are approximately 60 known galaxies. A typical region of the universe this size would contain thousands of galaxies. The Boötes void contains essentially nothing. The galaxies that have been identified within it are concentrated near its edges, not distributed through its interior. The interior is not quite a perfect vacuum. Individual atoms and molecules drift through it, traces of the hydrogen that permeates all of intergalactic space, but at densities so low that they constitute nothing in any practical sense. The mean free path of a photon traveling through the void interior is effectively infinite. Light travels through it without interacting with any matter for hundreds of millions of years. A hypothetical observer positioned at the center of the Boötes void would inhabit a sky nearly devoid of galaxies. In all directions, the nearest galaxies would be at the void's walls, roughly 165 million light-years distant. Their light would be severely redshifted by the expansion of the universe, faint and far, requiring instruments of considerable sensitivity to detect. In visible light, the sky would appear not dark the way it appears dark in intergalactic space, dark with the occasional point of a distant galaxy, but dark in a more complete sense, the dark of genuine emptiness. The nearest galaxy clusters, with their diffuse glow of combined stellar light, would be too far away to provide even the faint background glow detectable from within a galaxy supercluster. Cosmological models of structure formation predicted voids should exist as the flip side of the filament and cluster structure, but the Butte void, when first identified in 1981 through a survey of galaxy redshifts, was larger than theorists had expected given the age of the universe. In the time since the Big Bang, gravity has had approximately 13.8 billion years to gather matter into filaments and clear the spaces between them. The Boötes void is consistent with this process operating at its expected rate. But it represents the largest empty space that process has produced in the observable volume. It is the universe's largest known absence. The danger of the Boötes void is not radiation, not temperature, not tidal force. It is isolation of a kind that has no human analog. Any civilization that formed within the Boötes void, if there were sufficient matter in its interior to form stars and planets and life, which there likely is not, would be isolated from the rest of the universe by a span of emptiness that no practical form of travel could cross in any finite lifespan. The nearest civilization in the nearest galaxy at the void's edge would be tens of millions of light years away. Any signal sent would arrive at best tens of millions of years after dispatch. Any concept of communication across that distance would require civilizations stable over geological timescales simply to exchange a single message and response. The Boötes void is not dangerous in the way a magnetar is dangerous or in the way an iron rain planet is dangerous. It is dangerous in the way that complete permanent isolation is dangerous. A silence so total and a distance so vast that the concepts of contact and connection simply do not apply. The universe produces danger through abundance. Too much heat, too much gravity, too much radiation, too much orbital instability. And it produces a different kind of danger through absolute scarcity. The Boötes void is the latter condition made manifest at the largest scale that matter has yet organized itself to produce. It is not the end of the structure of things. Beyond the void's edges, the filaments and walls and galaxy clusters continue, the cosmic web extending outward in all directions to the limits of what we can observe. But it is a reminder that the same universe that produces Wolf-Rayet stars burning at 210,000 Kelvin also produces regions spanning hundreds of millions of light years where the nearest source of any light is impossibly distant. The most extreme environments in the universe are not merely different from familiar ones. They are different in kind, operating through mechanisms that have no terrestrial analog, shaped by physics that our everyday intuitions cannot reach. The glass rain of HD 189733b, the diamond interior of 55 Cancri, the iron rain of WASP 76b, the crystalline carbon planet orbiting PSR J7W19 1438, the neutron-dense magnetic storms of SGR 180626, the pre-supernova burn of WR 102, the gravitational architecture around Sagittarius A, the 330 million light-year emptiness of the Boötes void. None of these places care that they are extreme. They are simply what physics produces when it operates without constraint. That is, in the end, what makes this journey worth taking. Not the danger, not the spectacle, though the spectacle is real and vast. What makes it worth taking is the demonstration that the physical laws that govern the behavior of electrons in a laboratory on Earth, that describe the rate at which a pendulum swings and the path of a thrown stone, are the same laws that govern the behavior of iron vapor in the atmosphere of a planet 390 light-years away, and the precession of a stellar orbit around a 4 million solar mass black hole 26,000 light-years distant. The same mathematics, the same constants. The same forces, applied without limit across the full range of conditions the universe provides. They produce everything we have seen tonight and everything we have not yet found.